lighting projection in some very abstract context, and then discuss a special but very important case of it, which is called the EM algorithm for maximum likelihood with partial observations, which is really something of a much more general class of problems that we are now facing every day in machine learning. The EM algorithm itself is famous because it used to be the main method for doing maximum likelihood in cases of mixture models, like mixture of Gaussians, or all the cases where you have distribution which are not of exponential forms. But it's actually a very limited type of result because it doesn't guarantee much about the solution, just local conversions to some local optimum, which can be very far from what we want. So I prefer to show this larger picture and then show other applications of it in the context of coding theorems and in the context of graphical models. And so I'm here moving a little bit outside of the lecture notes that you have. Not much. I'll go back to this. So tomorrow I hope to finish this chapter completely, show you actually something about coding and description length already. The first, what we call the lossless or the noiseless source coding theorem. Actually, it connects likelihood with length, with code length. And then next week, we're going to run through some fundamental results in computational learning theory, PAC model, some extensions of the PAC model, some bounds on sample complexity, and some really the basic results, and the old results, the VC dimension and the PAC base bound. This is essentially what I want to show here. And then later, at the end of the course, I'm going to wrap up everything with the coding theorems somehow and connect them to learning. So it's a little bit crowded and messy because I'm introducing concepts from different places together, and I hope so. We really need to work on it on your own, otherwise it doesn't make much sense. And I'm aware of it, but I think it's eventually the picture is much more complete this way. So last time we showed, first of all, that in general the KL divergence between two distributions, P and Q, is convex in both P and Q. And I hope you now know what I mean by that. Which means that if you take a linear, a convex combination in both arguments, you only decrease. It's smaller than the convex combination of the DKLs in both arguments. And this is actually a fundamental property that we're going to use in many different places. And then I talked about projection. So I said essentially we can talk about two types of. So a convex function or a concave function. A convex function has a unique minimum if it's strictly convex, which means that the functions of the convex combination is strictly smaller than the convex combination of the functions. Strictly means that there's a strong inequality there if lambda is not 0 or 1. And this is equivalent actually to assuming that the second derivative is either positive, negative, positive definite in the case of convex functions, and negative definite in the case of concave functions. And concave functions are just negatives of convex functions, so they have a maximum, not minimum. So any strictly convex function has a unique minimum in a convex set. Okay? So if I have a convex set is something which includes all the lines that connect 2 points in it. In Rn, it's very easy to imagine. In the case of distributions, we know what we mean by convex combination probability distribution. It's also a distribution. And if this distribution is in the set, we said that this is a convex set of distributions. Okay? So the simplex, for example, is always convex, of course. It's actually has corners and it has linear boundaries, but it's still convex. and the sphere is convex. I mean, how many good sets which are convex? Actually, by the way, the surface of the sphere, not the ball itself, is not convex, of course. Because the line that connects 2 points, the shortest line, is not on the sphere. Okay, that's why things are getting more interesting in some cases. So in a convex set, D has a unique minimum. It's not really unique because it's only weakly convex in general, but has a minimum which may not be unique in a convex set with respect to both arguments. Okay, so if this is a convex set of distributions, then there's a unique minimum which we may denote by P star, which is sometimes called the I projection. I projection of a probability distribution Q on the set pi, which is going to be the distribution which minimizes this, if pi is a convex set, minimizes the dpq, and this is actually the projection of Q on the set pi. Okay, so there's a minimum like this, and we already saw that there's another projection, the maximum likelihood, for example, was a projection in the other direction. So we can also talk about the arg minimum of over, let's say, Q of dpq, where P is given and I minimize over Q. So this may also belong to some set of distribution Q. This is a different projection. It's a projection from the left to the right. And we saw this already. This was the maximum likelihood. The maximum likelihood is a projection of this type of the empirical distribution on our parametric family. Okay? Yes.
Just to make the analogy.
So this is something, just to finish it, in this Q star, which is, sometimes we call it the E projection. Actually, there's some confusion in, people call this projection different names. I'm using E and I. Later on, we'll see that this is actually something like E and M, but we'll see. Okay, yes?
So, to make the analogy clear, so to make the analogy to geometry, so the distributions are like points in space,
Yeah,
or
right.
vectors in space?
So
or
if we talk about a simplest set of distributions, so this is a set of distributions. It may be a little bit confusing for. So distribution, each one of these things, so let's say P here, P1 here, and P2 here. These are distributions over some sample space, or over some random variable or something like that.
Because when we say projection, we usually mean the projection of a vector.
Yeah, so you can think about a distribution as a vector in Hilbert says, if you want, in general. So it can be finite dimensional vector if X is finite. And it can be an infinite dimensional vector. So I hope this is not a big problem for any of you here. So we can think about vectors in infinite dimensional space. So those are functions, if you want. And functions are also vectors in the sense that it's a linear space. I can sum them. I can multiply them by constants. So actually, for distributions, it's a very special kind of linear space because they're normalized. So it's constrained. It's not just a general. They have some finite norm, in this case, the L1 norm, and they're all positive and so on. So it's a special case of functions, which are actually not as nice as we would like. In many cases, we actually like really linear spaces instead of distributions. This is, for example, what happened in quantum mechanics. So you move from distributions to amplitudes, and everything becomes much nicer. Yes? So Q in some larger set of distribution, which may be a parametric family. So this is also a set. If it's a convex set, this Q is another set. So, just to make everything more confusing, I'll denote it by big P, and this is by big Q. Okay, so this is a set which can be convex, big P. And this is another set which can be convex. If both of them are convex, then this minimization has a unique point. I have to be careful with this because the DKL is only weakly convex. Yes.
So P is the argument of the DKL of P and Q, but does Q have to be in the set phi as well, or in the convex set as well?
No. So in general, okay, this is exactly what I'm going to say in next. But so in general, we can have two sets. This is P, and this is Q, which do not intersect, may not intersect. And then indeed, I can define, for example, the distance of the set Q to P as the one which the 2 points in P and Q that minimizes the distance between them. So this is actually a generator in geometry. If you have two sets, you want to, if you have an Euclidean distance between two sets in Rn or whatever, and you want how do you usually define the distance between them? What is the distance between a point and the line, or a point and the plane? So usually what you do is the shortest possible distance. So in linear, in a plane and point outside of the plane is simply the shortest possible distance is the distance to the projection, to the linear projection, which is perpendicular, orthogonal. In L2, it's very simple. These are orthogonal projections. Okay, and if you have curved spaces, this minimum may not be so simple. And actually, even here, where D is not a distance at all, it's actually not symmetric. I can still play this game, and there's some point here which is closest to this, and some point here which is closest to this and this. So there's some D minimum, which will eventually be the arg min over both things. I mean, both P in P and Q in Q of this dpq. So this is going to be, so there's going to be some Q star here and P star here, which minimizes this. Okay? So in general, they might not be identical.
A question about that. So because D is not symmetric.
So the other way around may be different. Right. So it's unlike the Euclidean intuition that we all have in mind. Distances which are not symmetric may have different types of projection. Okay, so this is just the general idea of using, it's the beginning of something which we're going to extend only partly in this course, but maybe in other courses. We use these information measures like the DKL and all its relatives like entropy and mutual information and conditional entropy, and all these are different types of DKLs in some sense. We actually use them in many cases, in most interesting cases, as variational functions. We minimize them or maximize them. In this case, is minimize with respect to one of the arguments, subject to some constraints. And this is what's going to make it interesting. So usually we don't want to calculate it, we want to calculate only in a very special point, in a point which is extreme of something.
So regarding the non-symmetry, so P and Q are the sets P and Q are going to represent some sets in our problem. So how do we know which is P and which is Q? Because they're not symmetric.
Okay, so we have to know what they're doing. I mean, so in general, okay, this is not a symmetric function, and you have to know which of these two things you really want to make. So for example, maximum likelihood, as we said, was a projection of this on the empirical data, where this was the empirical, and this was the set, the class of parametric distributions. This projection is actually different. And it's very different because we take the derivative, as we will do in a second. In one case, we have P log P, and the other one you have P log Q, and it's a very different derivative. Okay, and we'll show you in a minute what we mean by this. Okay, so this was just this is the beginning of a big topic, which is sometimes called information geometry, which I personally like very much, but it's a little outside of the scope of this course. So actually, there's a lot of geometrical intuition that you can play with information measures like this, and many of them make a lot of sense in the context of statistical estimation and so on, and inference. Okay, so if you have this. Not all of you like geometry, but those who actually have the geometric intuition, this kind of things really help developing all sorts of new algorithms, and you know what you're doing and so on. So in principle, the algorithm, the family of algorithms I'm going to talk about, I think that let's say you start with some distribution here, and then you minimize the distance to this, you get another one, that's this one. And then you minimize the distance to this, and then you minimize the distance to this, and so on. And if, so you start, this is going to be T equal 1, T equal 2, T equal 1, Q1, P1, Q1, P2, Q2, and so on. So I'm going to do alternating minimization between these two sets. And eventually, if the two sets are convex, I'm going to converge to the minimum. This is something we can prove in general. But since we always minimize the same function, once with respect to one argument, you're always decreasing it. So it's a decreasing, monotonically decreasing function of distances. And since it's bounded by 0, it ought to converge. And now it may converge indeed if the two sets are intersecting. If there is a distribution in Q which is also in P, then it will converge to this unique minimum. And that's it. Otherwise, it will converge if the two sets are convex to the unique P and Q stars that are minimizing the distance. Okay? So in general, when we talk about alternating minimization, we usually have in mind this type of picture. Two sets where we minimize something between them. In general, we can also do it with more than two sets, and we may see algorithms like this, probably not, but we may, where we actually have several sets that we want to jump. Then things are much more complicated. You don't know much. You know only things like local convergence. Actually, in the case of non-convex sets, like in the EM algorithm, you don't know that you actually achieve the minimum because there may be several places that minimize locally, but not globally. Okay? Now, I defined a special set of distribution, which I call the linear. The linears, I divide this curly L is, I usually reserve it for Lagrangians, but keep it L like this. So, which is essentially a set, given a set of observables, as we usually call them, and A1 of X, A2 of X, and some set of functions, let's say up to AK of X. So this set of functions, you can define expectations. So like, for example, it can be X, X squared, X cubed, and so on. Then there'll be different moments of the distribution. There can be other functions like, I don't know, sine, cosine, crazy functions. I mean, something which is, for example, characteristic functions of some set. It can be 1 in some subset and 0 otherwise, and so on. It can be anything. Okay? So in general, this set is the set of distributions, usually unrestricted, but I restrict them by this. So this belong already to some simplex between the normalized distribution, but such that the expectation of this R is some numbers, some given numbers. For R between 1 and K. Okay, so essentially there's some, I can write it in a vector form, and the expectation of this vector A is a vector of numbers. So for example, I'm giving you a number, the mean, or the empirical mean. All the distributions that, for example, I can tell you I have a die has 6 possible outcomes, and I can tell you this particular die, I threw it, I don't know, 1,000 times, and the only information I'm giving you is that the average was 4.5. Okay, so the average of the number 1, 2, 3, 4, 5, 6 was 4.5. So you know that something is probably not right with this die. I mean, it should be 3.5, yeah, if it was balanced. So what can you say about the distribution in this case? Obviously, not much. So there are many distributions that have this 4.5. For example, it can be 4 and 5 alternating equally, only 4 and 5. Or it can be other things. So one of the interesting questions in statistics in general, I mean, okay, what is the most probable distribution, and what is the best guess? And this is going to lead us to this maximum entropy thing. I mean, so what can I say with this partial information? It's very small information, but it's telling me something. So this is the kind of question you want to be able to answer. It's a different type of inference. It's inference from very partial data. I mean, we don't have enough to really determine all the probabilities, but we would like, in some intelligent way, to infer it anyway. Yes?
You want the distributions to have the support also?
So so of course there is suppressed here, there is X here. And of course we assume that all of them have, so there's some support. All of these functions are functions of X over which we have distributions on. Like usually, just to make things simpler, we assume that they all have the same support. When I say functions have the same support, so of course they must have the same support. I'm not necessarily saying that they don't have a smaller support. They can have 0, but they're all defined on this. Okay. Now, as I said, I mean, sometimes this is an empirical data. I mean, often in the case in practice, what we're given is the empirical mean and the empirical variance of something, which means okay, there are many possible distributions. What is the most likely distribution in this case is given the empirical data. And we know already that the maximum likelihood is simply a projection of the empirical data on my set of distributions. And now I actually want to talk a little bit about the other side, the other type of projection. Now, LA is trivially convex. If anybody is not sure about this, think for a second. By construction. So of course, so there is a unique projection. Actually, we have to be careful here. This set may be empty if those constraints are inconsistent with each other. For example, I can give you x, the real numbers, and I can give you two values. For example, x is 4, x is 1, and x squared is half. These are two constraints on so these are inconsistent constraints. Why? There are no distributions that obey them. Yeah, the variance is negative. Okay, so in this case, I mean, it looks like a very simple type of constraints, but they're inconsistent with each other. So there's no distribution that obeys these two constraints over the real numbers, because the variance will be negative. Okay, so this seemingly naive type of constraints can be tricky. And of course, if A's are linearly dependent, then of course they must be consistent. I mean, so I may calculate one of the average from the others, and if they are not the right numbers, then it's inconsistent, and so on. So usually we assume that the A's are linearly independent. It makes life a little easier, and that the constraints are consistent. So this is L in convex. It can be empty. Okay. So if it's not empty, usually there exists such a unique minimization, and I argued. So we had a claim that I want to prove now, that if I take any distribution Q of X, proper. Let's ignore for a second the issue of support. It's a bit tricky. So for any Q, there is a P star, which it's the argmin of D PQ, where P is in this linear set A. Okay? So according to what I said before, there is such distribution. And I just want to convince you that it's indeed of an exponential form. So let's ask, what is it? Okay. So the claim is, of course, that P star is Q with some normalization, which is actually an interesting function of the other variables here. E to the sum of some parameters, let's call them lambda, because I still want to distinguish them from theta. Lambda r, AR of X, where R goes from 1 to K. Then this is this P star, or the I projection. It's the I projection of Q on LA. Okay? So this is something not hard to prove. For anybody who knows the method of Lagrange multipliers, I hope it's all of you. Okay, so the proof is simple, but I have to show it once at least. Question? Too quiet, yeah.
Why is LA convex?
So L is convex because if you take, again, what do I need to show? That if Pn1 and P2 belong to LA, then lambda alpha P1 plus 1 minus alpha P2, where alpha is between 0 and 1, is also in LA. Those expressions are linear. Okay? So it's easy. So I want to say that the projection of any distribution Q, which may or may not be in the set, but let's say it should be actually outside the set, doesn't really matter. So any Q, this arg minimum exists and it has this form. This is the claim. It's what we call an exponential form, but the A's are going to be my sufficient statistics or my functions of the space that appear here in the exponent. Okay? So why is this true? It's really, I just want, since last time it seems that I lost you at some point, I want to make sure that you all know why is it true. Sorry, I'm not terribly well today, so what do we do? So using Lagrange multipliers, so this essentially is a minimization under constraints. What are the constraints? Precisely these expectation values. Okay? So how do we in general solve optimization problem under constraints? In cases like this, where we assume that the derivative is well defined and inside the set. So we define something which we call the Lagrangian function of P. So P is the unknown here. So let's write it as the DKL. Let me write it explicitly as a sum. It can be an integral for the same cost, but just to make things life a little simpler. So this is this dpq. Okay? And then I want to minimize this, but in order to impose the constraints, I introduce Lagrange multipliers over all the constraints. And if you don't know why this is true, come to me later, actually. But I do hope that you saw it somewhere. So it's plus the sum that, how did I call it? R go from 1 to k of px ar of x. If you really want to be strict, you have to put this value. And then in order to impose this constraint, to impose this constraint, I have to be a little more careful. So there are two sums here. Okay, so there's sum over r, and then I put a Lagrange multiplier lambda r here, and then I put a sum over x, p of x, ar of x, and then minus this value. Okay. So this is the constraint. This function has to be 0 in this case. Okay. And imposing it with the Lagrange multiplier, and actually we have to be, in general, even more careful because there's another constraint, which is the fact that the distribution is normalized. Okay? So let's call this lambda 0. Okay, so there are sets of Lagrange multipliers. The first one is the normalization. So first of all, you see this is essentially the same type of constraint where AR is just 1. Okay, so you can include it in the set if I want. But it has actually a special, since this is always true, this is of course going to be related to this z. Lambda 0 is just log of z or something, minus log of z. So if you don't see it. So anyway, this is what I have to do. And of course, now I treat it not only as a function of p. P is in this case the dimension of the distribution, dimension of x. Since I imposed the normalization already, I can treat all of them as independent. All the p's are independent. Okay? And I can, so I essentially, I just introduce another vector of parameters here, which is the lambdas. All these k lambdas, k plus 1 lambdas, if you want. Okay? So now what the method of Lagrange multiplier is telling me, the optimum should be at the point this gradient. In general, it's not, if p is a function, I mean, if this is a continuous variable, then you have to be careful when you say gradient. So some people call it functional derivative, but it's the same idea. So I actually take the derivative with respect to every value of p, every possible value of p. So this is for every x. For every x, this should be true. And of course, I added those new variables, so this L to the lambda, actually here is also a vector in a sense, for any one of them should also be 0. So I can say R is between 0 and k. Okay, so this is essentially the condition for optimum. Anybody is not with me here? I mean, I really want all of you to know what I'm doing. Okay, so essentially, this, as you all know, the only dependence on lambda is here. So these equations are trivial. They're just the equations of the constraint. Okay? So lambda has to be chosen such that this is satisfied. Usually, so it's very nice. So this is really the interesting part. So the interesting part is, since I'm taking the derivative with respect to p, sorry, there's a quality here. So I take it for any given x. For a given x, I take the derivative with respect to p, so the sum is going to disappear. Okay? Because it's in a particular x. And only the thing that depends on this x I'm going to take the derivative. So what I'm going to get here is that p log p, the derivative of p log p over q, the product of functions of p. So the first one is going to be simple one, log p of x over q of x. Simply take the derivative of this as constant. And then the other one is the derivative, it's p times the derivative of log p. What is the derivative of log p? 1 over p. It's a ln, yeah, for that matter. So, so this is plus 1, because the other one, log q, is independent of p. Okay? So I have log p minus log q. Take the derivative of p times 1 over p, it gives me 1. Okay, that's all is left. So this is the derivative of the DKL. Very nice. And then, of course, the derivatives of these are simply going to be the lambda r times AR. Okay? Plus lambda sum over r. Allow me to write it like this. Lambda r AR of x. Of course, this doesn't. I take the derivative with respect to p, so you can, strictly speaking, have to write minus AR here. But no, okay. So this falls. Okay. This little a, you see that we usually omit it, because if I take the derivative with respect to p of this, nothing happens. Okay. So we can actually write the Lagrangian as we usually do without actually explicitly writing the value of the constraint. Doesn't matter. It's a standard question I have, so that's why I do it carefully once. And I just use the notation H0 of x is 1, just to make sure that you know what I mean. Yes? Question? Doing it very, very slowly. So this should be 0. Okay, and that's it. So this is the derivative, I'm sorry. This is dl to dp. Okay? So it should be true for any x. So up to signs, I mean, actually, we usually take the Lagrange multiplier to be negative, but up to signs, so we see, I have to be more careful here with the sign, it doesn't matter. So with this convention, I can swallow the 1 with the lambda 0, and ignore it, essentially. So you just see that log p of x is just a linear combination of the x's, log p over q. So this immediately gives us that p must be q, and then I can take all the constants as into this normalization factor, So the exponent of 1 plus lambda 0 is going to be 1 over z. You can always do that. And actually, it's useful to think about this as a function of the other, those k numbers. Because this is as some of you know, it's a partition function, or a generalized partition function. And the derivative of this z with respect to the lambdas is actually going to give us the expectation values, as you can see immediately. So this is p of x is now, for any x is this, and since I took it out of the exponent, I have the exponent of the minus sum of the lambda r. Okay, so this is really very slow derivation of this. Any question on this? Now notice that just to make sure that z, this function z of lambda 1 to lambda k, is simply e to the 1 plus lambda 0 when I think about this as function of the others. Okay? Now notice, so this is just the definition, notation view. And it's also, we usually call it the partition function. Just to make the physicists happy. In some other contexts, in mathematics, it's actually called the moment generating function. It's related to something called the characteristic function, which is a Fourier transform instead of it's related to it in somehow. And so there are many different functions, the Laplace transform, many different ways of getting to this type of function. It's actually very, very important in general. Okay? Now, one easy thing to see, so this distribution has a very special form. If you've seen it before, it's of exponential form. But precisely, I think I can think about it as exponential form if I think about the lambdas as my parameters, or some functions of my parameters, and the a's as the sufficient statistics, if you remember, as those functions which eventually going to lead to sufficient statistics. So this particular form, a are sufficient statistics, if you consider lambdas as the parameters or functions of the parameters. By the way, so the exponential form written that way, where here you have exactly linear function of the lambdas, in this case we call the lambdas the natural parameter of the distribution, the natural parameterization. It may be more complicated. So the natural parameterization are actually very easy because of these nice properties that you can easily verify. So for example, the derivative of ln z with respect to the lambdas is simply the derivative of lambda 0 for each of these lambdas, which is just the derivative of, and so there's a minus here. So this was a minus here, I'm sorry. The way I defined it, no, I'm not sure about the sign. So this is simply this expectation. This is easy to check. And actually, you can even see something nicer, which is the second derivative of this with respect to lambda r, lambda l, let's say, some two lambdas. And what do you think this will be? Yeah, it's going to be the covariance, or minus the covariance. Depends again on a r, a l. Covariance. It's actually it's covariance. So I subtract the mean. It's in general these things are going to generate higher and higher moments. So higher derivatives are going to generate higher moments, and this is why it is sometimes called the moment generating function. It's actually going to generate high cumulants, but it's all right. So. So this is nice. So this is why this function usually tells us all the story. If we know how to calculate it, we can calculate many things that we are interested in, all the expectation values and all its variances and so on. Okay? Check this.
So
So the lambdas, so in the classical case where, there's only one constraint, the energy, so lambda is simply beta, 1 over temperature. If you take the constraint, let's say, to be the volume, you get the lambda to be the pressure. If you get the constraint to be a chemical number of particles, you get lambda to be the chemical potential, and so on and so forth. So the lambdas are only all the intensive, nice thermodynamic functions that we like. Temperature and alike, other chemical potentials, pressure, all these nice things. If you take, for example, constraint on angular momentum, you get some other nice quantities. So they're all natural and very interesting. These are the physical entities which you really care about.
Right, in physics we usually have one constraint.
Usually, that's not always true. I mean, if you take a grand canonical ensemble where to get the Helmholtz, not the Gibbs free energy, you get the pressure, you get the chemical potentials, it's not true. If you really look at thermodynamics more carefully, all those things are there. Sometimes they want to constrain, to leave it in open, leave the number of particles open and so on. You have grand canonical, all these thermodynamic potentials are some sort of constrained optimization. So notice, by the way, that if Q is uniform, so if I can take Q to be uniform, then, as you know, this minimization is precisely like maximizing the entropy. Okay? So in particular, a special case, if we can take, actually, even if we can't take, we do it, Qx to be uniform, I actually want it to be clear. So then age of x was simply defined, as far as I'm concerned, as ln of the cardinality of x minus the d of p of x to the uniform. So in this case, this arg min of d to the uniform over p is equal to arg max of age of p. And this special case is called the maximum entropy distribution. Which has very important. And so in physics, in most cases, we don't have this Q, or we omit it, assume it to be uniform, which means that there is some sort of microstate in your space where you can assume that they're equally likely and so on. You have canonical distribution over them. There are all sorts of assumptions behind this. But here, in general, we don't want to assume it, so we always remember that there's actually a prior here, and I personally don't like this maximum entropy thing without. So maximum entropy is a special case of this minimum decay. Okay? Now, notice, by the way, that this has a very nice form. So this P of x is Q of x up to normalization multiplied by some correction. So this exponential correction is something which is due to the new information I gave you. I gave you information about those expectation values. It's modifying my prior knowledge. You can think about this as prior. And the whole thing is some sort of posterior. And this is how the posterior was modified due to the additional information I gave you. Okay, so this is the most likely of the most probable of the one with minimum DKL or with the maximum entropy. At this point, you really don't know why should I care if it's the minimum DKL. But we'll see later on that this is actually going to be something very powerful when we talk about large deviations. We'll come back to this in the course. When we talk about information theory again, and typicality and things like this, you'll see this minimum DKL actually is a very powerful argument. I mean, this is in some sense, the most likely or the most probable distribution under some assumption. So this closest in the sense of D is not just because I like D. It has some very nice interpretation as the one with least assumptions about the data. In general, we say that the maximum entropy is like this. So the maximum entropy is a distribution which makes the least possible assumptions about the data other than the observation. It's precisely the distribution for which our observations are sufficient statistics. Okay, so if I go back before the break to this question about the dies with expectation 4.5. So what is your best guess in that sense? So the maximum entropy distribution in this case is going to be exponential in I, because I'm actually, so this example, I have a sum of I goes from 1 to 6, pi times I equal 4.5. So this is and of course I have also some pi equal 1, and all positive. Luckily, by the way, I don't have to worry about positivity, because the exponent is always positive. But in principle, there are other constraints. I mean, the fact that pi should be on the simplex, for some good reasons that we can appreciate later, the entropy is always generating a positive number in this case. So in this case, you can calculate it yourself. It's not so easy to do it analytically. But so the maximum entropy distribution, in this case of I, is going to be some normalization e to the minus some lambda I. Where lambda in this case is positive, so this is exponential distribution. And of course, I have to choose lambda such that this constraint is satisfied. Exactly. Okay? So analytically, it's not that easy, by the way, to find the optimal lambda, but there are reasonably good algorithms for doing this. I mean, to finding maximum entropy distributions like this. One of them is actually an iterative algorithm on its own. It's called the iterative scaling, and there are many other algorithms for finding the lambdas. So in principle, it's a numerical problem. It has a unique minimum. You can find it by some alternating iteration as well. Okay, so in this case, if I give you this information, this die was tilted. Dice was tilted in the wrong direction. It has a 4.5. What is the probability of getting 6? So this is an ill-posed question in principle. You don't know. But if you assume that out of all possible sequences that generated this 1,000, what is the one which captured the most volume? So this is precisely the maximum entropy. And actually, allow me one more minute. In this case, I actually know the distribution, so I can actually calculate it. I mean, the number, what is the probability that I got n1 times 1, and n times, and 2 times 2, and so on, up to n6 times 6? This is my empirical numbers. So out of all possible sequences of thousands of 1,000 rows of this die, the probability of getting this particular, the number of possible ways of getting this particular number is what? Is n factorial times n1 factorial up to n6 factorial. Just reminding you. Okay? So this is essentially the volume out of all possible ways of getting. Now, if I'm telling you, so this is the number of possible sequences anywhere that will generate this particular partition. Okay? Now, something you already know, just remind you, the log of this number, or the ln of this number, n factorial divided by n1 factorial up to n6 factorial, what is this? So you saw it in one of the exercises a long time ago, in the case of the number distribution. You use the Stirling approximation. So you know that log n factorial, or ln n factorial, is approximately n ln n minus n, and I don't care about the prefactor there. There's a square root of n, 2 pi n, which at this point I ignore. Okay, so this is the leading term. This is Stirling. And if you just plug it here, you get immediately that this is simply the entropy of the distribution n1 over n up to n6 over n. So this particular distribution, this number is simply this. Check it. You saw it already. I just reminded you. So this gives you an intuition why this maximum entropy is so important. Because among all, if I think of all of those possible sequences of 1, 2, 6, 3, all the possible 1,000 sequences, it's not 1,000, 6 to the 1,000 sequences of possible die throw, out of the volume, the number of this, if I consider these numbers to be, all the sequences to be equally likely, the partition that will capture the most volume is precisely the one which maximizes the entropy. Okay, so this is actually leading immediately to Gibson-Boltzmann. Or actually to the foundation of statistical physics. I mean, so they really thought, okay, out of all possible configurations of my space, what is the one which is most likely? If n is large enough, it's going to be completely dominated. Most of the sequences are going to be close to the maximum entropy. And this is the beginning of what we later will call typicality or large deviations or things like this. So this is something you should be able to see. So again, the maximum entropy distribution is precisely the distribution which maximizes this volume. Okay? So this is some intuition why this is such an important concept. Okay? Okay, I'll take a break now. And if there are questions, this is time to ask them. Okay, I'm going to move to EM.
אני יכול לגזור בתוך אינטגרל כל הגבולות תלויים במה שאני רוצה. גם בתוך שם. אינטגרל סכום. אפשר להבטיח אתה זוכר שיש תנאים, אבל התנאים לא הם טריוויאליים. אתה יודעת שאם הסכום קיים, הגבולות שלו לא תלויים בדבר הגדול יותר. כן, בדיוק כמו אינטגרל. אינטגרל זה סכום אינסופי. אז מה שנכון סכום אינסופי, אינטגרל יותר גרוע. הסכום הזה יתכנס ושהם נמצא היטב, סכום בין אינסופי. תלויים בפרמטרים, או תלויים בדברים שונים. אם הגבול כזה, צריך למצוא גם את הגבול. פונקציה מורכבת. למדה אפס הוא נורמליזציה.
כשאנחנו פיתחנו את זה, אנחנו קיבלנו 1 פלוס למדה אפס כפול A.
למדה אפס היה כפול A0.
A1, בדיוק.
זה למדה אפס. מה זה Z? כי אני צריך לנרמל את זה. Z היה סכום על ה-X של QX, E בחזקת סכום ש-R הולך מ-1, חלקי של למדה R זה Z. זה גם E בחזקת 1 פלוס למדה אפס. עכשיו זה אני יכול לחשוב עליו, להגדיר אותו. לא רוצה לחשוב על זה כפונקציה, זה לא פונקציה של X, זה תלוי בלמדה. אני יכול לחשוב על זה כפונקציה של למדה פרמטר. גם על למדה. זה פונקציה, אתה רואה את זה? כשאני גוזר את זה לפי למדה, אני לוקח את זה. מה זה לגזור את למדה זה? למה זה נכון? זה הנורמליזציה של ההתפלגות הזאת. זה נורמל את הלאחד. זה נורמל אחד. מסתכל את כל הערכים ומחלק את זה. זה גורם לנורמול. ככה מוגדר, גורם לנורמול זה סכום על כל הדברים הלא נורמליים. עכשיו, קח את הפונקציה, את הלוג של הפונקציה הזאת, תגזור את זה. אתה גוזר את לן D, זה נותן 1 חלקי Z. אתה נגזור את האקספוננט. כשאתה גוזר את האקספוננט לפי למדה, זה מוריד מהאקספוננט את ה-A הנכון. רק אותו. לכן תקבל סכום, אחרי שגזרתי לפי למדה בתוך הסכום, ה-A ירד חזרה, וקיבלתי סיבוב סופר. הלן ניתן לי את 1 חלקי Z, ניתן את הנורמליזציה. וזה עצמו יוריד לי מהאקספוננט. תגזור פעמיים העיקרית, קצת יותר טרקי. גוזרים עכשיו את זה לפי למדה שני, הגזרת הראשונה היא זאת, אני גזור את זה לפי למדה, זה יוריד את הלמדה השני מהאקספוננט, את ה-A השני מהאקספוננט. אני תקבל פה מכפלה של שני A, אבל כן אפשר צריכים לגזור רק את ה-Z, לכן זה יוצא באמת, הדבר הזה זה A מינוס A L מינוס A מינוס R, מוכפל ב-A R מינוס A R מינוס R.
תוכל את זה בגלל הסכום?
תוכל את זה בגלל הסכום, כן. הסכום נשאר. זה בעצם הפתרון של התרגיל הזה. זה מכפלה. לא, סליחה, התכוונתי לזה, כן. התכוונתי לזה, זה הקובריאנט שלי. אתה רואה שמופיע שם, אם אתה עושה את זה נכון, אתה רואה שמופיע המכפלות עצמן. זה תרגיל שווה לעשות את זה. זה טריוויאלי, כן. עד עכשיו. לעשות את זה לגזור את זה. אבל לגזור את זה לגזור את זה שכתוב פה כבר AR. נשים לב שאני אגזור לפי למדה, אנחנו נגזור גם את G לפי למדה וגם את ה-A לפי למדה. וגם את ה-A. אני גזור את ה-Z לפי למדה, אני אקבל שוב את ה-expectation.
היה עוד משהו
במקרה הפשוט שיש רק למדה אחד שעליו גדי שאל, אז זה פשוט נגזרת שנייה. באופן כללי זה מטריצה, מטריצה קובריאנט. הנגזרת השנייה נותן לך בדיוק את הוואריאנט. לא ראיתם בשום מקום פונקציה יוצרת מומנטים או דברים מסוימים?
שאלות בשנה שעברה.
או אני יודע, איך קוראים לזה, פונקציה אופיינית, אני יודע,
קומונל ג'נרל.
הקומונל ג'נרל. אז זה מה שזה. אפשר לחשוב על זה כסוג כטרנספורם לפלאס, אם אתם מהנדסים. אפשר לחשוב על זה כ... אני יודע שמתמטיקאים אוהבים טרנספורם פוריה של ההתפלגות, לא טרנספורם פוריה. אתם קוראים פונקציה אופיינית. טרנספורם פוריה של ההתפלגות זה גם כסוג של...
רגע, אז מי פה הקומונל ג'נרל?
אז זה זה הקומונל ג'נרל. כי מה זה? זה הלנדבי. אתה רואה שבמקרה של שני הראשונים תורת קבוצת קומולטית, זה המשיך לתוך קומולטית. במקרה הגאוסי, כן. עכשיו, אין לך יותר משתי קומולטים.
יש שאלה לא קשורה ישירות לקורס.
כן, אני רוצה כמה שתי דקות, אני רוצה להמשיך.
אז ברגע אחד, יש לי בעיה, אני, לצורך העניין, אני לא יודע את כל הסטים רק כדי שנגלה לפואנטה. נניח שיש חצה רנדומית, שלוקח מישהו, ואני יודע רק את חלקה, ואני רוצה להשאיר את זה. אני מייצג את הקונקטיביטי של רשת, יש לו איזה מבנה בלוקים. ואני רואה באקראי תמונה מתוך המטריצה המלאה, ואני רוצה להשלים את
זה מאחר אנטרופי הוא שיטה מאוד טובה לעשות את זה. אתה רואה אינפורמציה חלקית? כן, זה בדיוק על זה, אז באמת, זאת אומרת, אני לא יודע איך למלא את האינפורמציה של הריב, אז אני אקח את המספר של אובזרוויישן שיש לי, otherwise it's too much.
יש לי איזושהי פונקציה.
זה לא תמיד טוב, כי אתה רוצה את המספר, זה לא מאוד טוב. היא לא תהיה פעם בית השני, וזה מלא אותה.
לא,
כל הערכים זה לא
אני אומר, המטריצה החלקית היא ספרטנית.
כן, בסדר, אז מקסימום אנטרופי זה לך את המטריצה הסבירה ביותר שלו, במובן הזה.
כן. טוב, אבל רק הדבר האינטואיטיבי שאני לא מבין זה שאני יודע להגיד משהו על הסטטיסטיקה של החלק הזה, איך אני יודע להגיד משהו על הריאליזציה של החלק הזה. נכון, אני יכול לשים...
התוכלות שלך ידועות, אתה לא יודע במה יצאו. אז זה בדיוק העניין, אתה רוצה למלא את זה בהנחה הכי פחות כזה.
זה אולי נקודה של איפה רואים פה את מה שאמרת לגבי זה שזה הדבר שיכול נניח פחות לגבי
אז אני לא אמרתי את זה על הסוף, אנחנו נראה את זה בצורה יותר שלמה שאנחנו מדבר על המשמעות של D כאינפורמציה, כאור סיור, כל הדברים כאלה, כאור קוד, אתה תראה שזה בעצם הדבר שמניח את הקידוד הקצר ביותר של מסוים. אבל כאן אתה כבר רואה את ההתחלה של זה. אני אמרתי לך שהאנטרופיה מודדת את הדוק של הרקע. מה שהאנטרופיה זה למצוא את הפעילות נשק של מרחב מהצדדים. זה האנטרופיה הדינמית. זה מה שבולצמן קרא לוג אומגה או לוג W. כלומר, זה לוג מספר המצבים. עכשיו, לוג מספר המצבים הוא בדיוק זה. אם אתה...
טוב, במקרה של מצבים בינאריים זה סתם...
זה סתם בינומי.
זה מולטינום.
זה מולטינום. אבל במקרה הבינארי זה האנטרופיה הדינמית. עכשיו, זה מידה מאוד חשובה. כי הדבר הזה...
מינוס לא.
לא, זה לא מספר מצבים.
אוקיי.
כאן הכל חיובי. עכשיו, זה יהיה כאן מינוס. עכשיו, העובדה היא לא רק שאתה רוצה, זה מקסימום אנטרופי זה לבחור את המחיר בנפח עם כל המשפטים האלה זה בדיוק אין גדול, יש
זה שה-Q הוא שטוח.
Q הוא שטוח. זה לכם, Q לא שטוח, זה רק נותן לך זה פקטור של Q, זה לא שונה הרבה.
Q לא שטוח זה כמו שדה חיצוני, נכון? כמו משהו כזה.
שדה חיצוני, יש לך כאן ייעוץ על השדה גם. אתה יכול לחשוב על Q בתור פוער, יש לך מערכת קוונטית, יש לך ניזונים למצבים שאתה לקחת בחשבון, כל מיני כאלה. Q יכול להיות, מערכת קוונטית יש הרבה, יש לך ניזונים, יש לך סימטריות,
אני משקיע לי את המצבים.
אבל באופן כללי, לוג מספר המצבים הוא בדיוק האנטרופיה, וזה מאוד מאוד מרוכז.
זה פונקציה מאוד חדה.
יש שם פקטור של n באקספוננט. ההסתברות הולכת כמו e בחזקת n האנטרופיה. ולכן ש-n גדל אתה מתרכז חזק מאוד ליד המקסימום. לכן בגבול התרמודינמית זה היחס חשוב. נראה את זה בפרט תוצאה אסימפטוטית, שאין מגדול, אז כל האנטרופיות יכולות להן למות. כמעט כל הנפח מספר תוצאה.
טוב, יכול להיות שאני רוצה לפגוע איתך זמן...
אלה דברים שאני אוהב לדבר עליהם. טוב, בואו נמשיך.
אוקיי, מה שקלטתי...
קצת סטיתי עם הניירות שלי, אבל לא.
What is the name of the curly L thing? What is, like, how would I look for that on?
Well, I'm actually using here somewhat not... I'm using this particular tutorial which is this distribution.
I mean, it's just
It's a linear space distribution which is constrained, determined by expectation. Okay. So, but this is not a very easy to use. Okay.
אני לא מבין עדיין, אני מבין מזה המוגליזיישן, אני לא מבין למה זה שונה מזה. כי כשאני מפתח פה אני מקבל את זה.
לא, נכון, אתה מקבל את זה, אני פשוט מגדיר לה, זה סימון. למדה אפס היה אילוץ הנורמליזציה. הוא מופיע באקספוננט. יחד עם האחד הזה ששאול. יש לי 1 פלוס למדה אפס, זה קבוע. לא תלוי ב-X, נכון? אז אני יכול לקרוא לזה, לקרוא לכל זה, זה במינוס 1. ואז אתה רואה שזה קבוע שכל מטרתו זה לדאוג לנורמליזציה. לא נותר אותו מפורש לנורמליזציה. אז למדה אפס רואה שזה לא גבוה. עד כדי, אני אקרא לזה למדה אפס. אז הלמדה אפס הזה הוא נורמליזציה. הוא לא בנורמליזציה, הוא אופנין אפס. הוא יושב באקספוננט. אני רוצה לחשוב עליו, אוהב לחשוב עליו, זה משהו. Okay, so please call everybody. That's our entertainment. כן, היה Christmas, מה אני אעשה? Okay, tomorrow, as Noga already told you, I'm going to take 1 hour from here, because it's clear that I'm not going to finish what I want, and I simply cannot go on with this forever. So, and tomorrow we really finish it. Okay, so this was a very long aside. And I know that some of you actually work with statistical physics and may see a lot of similarities to other things. Statisticians among you may work with cumulants and moment-generating functions and Laplace transforms, and all these are very similar, all related. Okay. So notice now is what we found, that if you have expectation values as observation, the projection of the set of these expectation values, so projection of LA generated an exponential form, the projection on any Q on this LA generated an exponential form. So essentially, if you think about it this way, I mean, so we have this LA, which is a convex set of distributions, and we had this Q, and what we did is this I projection, or minimizing this DKL, with P in L, generated this P star, which was this exponential form. And this is precisely the distribution for which the A's are sufficient statistics. Okay, so now if I go back and try to estimate my expectation with respect to P star of the A's, they're of course going to be satisfied. So there's no really much point in terms of projecting further, because actually I found a distribution in the set LA, so P star is in LA, and one projection gave me the answer. Okay, but what happened if you don't have sufficient statistics? So now I'm going to play another game. I'm going to twist it. So let's say that I have a parametric distribution, let's say Gaussian, I don't know, something, and I'm actually giving you information which is not sufficient. So what do I mean by not sufficient? So we'll see immediately some special case where you have hidden variables, and you have partial, you have hidden, you have observed variables, and they're not the same. So this is going to be a special case of what I'm going to say now. But so in principle, you can have, so in this case, the expectation A was a sufficient statistic precisely for the class for p theta, which was exponential form, which was of this class, qx over z e to the minus some theta r ar. So this is so now I'm going to reverse the logic. Imagine that you have an exponential, some family, but I'm not giving you sufficient information. I'm not giving you sufficient statistics. Okay, which means that I'm giving you some partial information, which is not enough to determine the parameters. Okay, so this is a general problem. It's a very important problem. I mean, we have partial observations. So, for example, I'm assume that your family is Gaussians. So, what are the sufficient statistics for Gaussians? The first and second moments, okay, or the mean and the variance, or something like this. These are sufficient. If I give you the mean and the variance, one projection will give you the right Gaussian. And I assume that I don't give you the mean and the variance. I give you the third and fourth moments, or something like this. So it's not good. I mean, these are not sufficient statistics for this distribution, but it's some information. Okay, there's some information there. I can give you moments of some other functions which are not going to determine the mean and the variance. So what can I do then? So think about it. Okay, so then I have one class of family of distribution which obeys my observations, and another class which is the parametric form that I'm trying to estimate. They are incompatible. So this Q and P are not overlapping, which means that there is no real one observation in the data. So what would you do then? So essentially, the generals, I'm not going to spend too much time if I really want to go to EM, but in general, this P and Q, this is going to be a parametric form. And this is going to be an observation, which are usually some sort of expectations of something, empirical expectations. Actually, without loss of generality, this is a different issue. I can assume that my observations are always expectations with respect to some distribution. Even if I give you one sample, I'll give you some very crazy function. And so this is some sort of an LA like this. And this is some P of theta. But the A may not be sufficient statistic for the theta due to all sorts of reasons. I'm giving you the wrong function. So what can you do? So this is precisely where you want to play both games. I mean, here I projected it once and finished the game because P star was already there. But if P star is not of the form that I want, so if one is exponential with respect to one set of functions and the other one is exponential with respect to another set of functions, so the only thing I can assume is, okay, let's iterate between these two sets and find the one here which is closest to this set of observation as possible. So how do I do it? Essentially, what I do is it's made out of two steps. One step is, okay, I don't know the sufficient statistics of my data because I'm not giving them to you. I'm giving you some other things. So let's assume that I have some distribution here, and then estimate in the best possible way your sufficient statistic. So what would you do? So at this point of the course, we should also say something like conditional expectation. Let's take the expectation of my sufficient statistic conditioned on what I know. This is the best you can do, at least in the least square sense. Actually, in a slightly more general sense, in the DKL sense also. So the one that will minimize the DKL to my set conditioned on my knowledge is precisely the conditional expectation. So the best that I can say about my statistic is let's average the sufficient statistic conditioned on my data. Okay, so this is really a very general philosophy. This is something we want to call the E-step. So given the observations, let's find the averages of, let's say that the observations are not A, are B. Okay, A. I already wrote A. So A are observations, but here there are sufficient statistics. Assume that there are sufficient statistics, but let's call them B's. Okay, B's of X. They're not necessarily the A's. So what would you do? If there are sufficient statistics indeed, you will take the conditional expectation of B given the expectation of A.
So this is called conditional expectation. Okay. Expectation of the sufficient statistics. So this is a little bit abstract, I know. So we'll show in a concrete example in a second. So in principle, if you don't have what you want, you guess it in the best possible way. And guessing it in the best possible way is, okay, given what I know, let's minimize the DKL with respect to this knowledge. So I'm telling you that minimizing the DKL in this case is going to be exactly the conditional expectation, just as happened, by the way, in the L square norm. So there's something in common between the DKL and the L square in this sense. Both of them are going to give you expectations. We're going to see this maybe more explicitly later on. So then I get, I project this here, estimate my statistics from this projection. And then I estimate my distribution better, because now I have a new estimate of the true sufficient statistic. But if these are the true new estimates of sufficient statistic, I have another, now solving the maximum likelihood of the sufficient statistic problem. For this one is easy because I know the sufficient statistic, but this may generate another set of expectations. If I now conditionally take the conditional expectation of this one, will generate another set of expected sufficient statistics because I change the distribution. So this is precisely what happens in this alternating minimization problem. So I guess based on what I think here, guess the sufficient statistic, condition on what I know. This is one projection. And then now I have a new estimate of the sufficient statistic. I have a better guess of my distribution. And then I use the E step again to condition it on what I know with this new distribution, and so on and so forth. So essentially, I get an alternating algorithm, which you can call so start with some P0. Okay, it's the best I know at this point. If the two sets are convex, no, it doesn't matter. If both of them are convex, you are going to converge. But if there's some non-convexity there, it does matter. It matters a lot, because it may converge to different places. So start with P0, and then estimate in some sense, this is Q. So this is this type of LA, as I said. And this is some sort of parametric family. Not necessarily exponential form, but can be parametric form or some other. If it's exponential form, it's a lot easier. So this should be an easy problem. And now what I do is first, estimate the sufficient statistic conditioned on what I know. So let's say if this is an exponential form, there are sufficient statistics. So then it's easy. So estimate the sufficient statistics based on what you know. I write it like this, and this is what you call the E step. So this is some sort of expectation, E counts of expectation. So I estimate what I don't know based on what I know, because now I have a distribution, a full distribution. But then, so I get another set. So from B, get another, I should write it more carefully. So the E step is minimizing, take the arg minimum over Q in LA of D PQ and P0 Q. Sorry. And what I want to say is the following. Pk plus 1 is going to be the argmin with respect to P of dpq k, and qk plus 1 is going to be the argmin, as I said before, I wrote it somewhere, of the pk plus 1 over q. So this particular set of alternating projections is in general true if I have partial information. If I don't know that my set actually intersects my constraints, and all I can do is guess this, conditionally expect this one, then guess it again, conditionally expect this one, and guess it again, and so on, and hope to converge. So this is some sort of a generalized form of what we call the EM algorithm, or the expectation maximization algorithm. But what I want to do now is to restrict this to this very special case. Oh, okay, I wrote it already here, so this is what I mean by this. But I do it in iterations. So I start with some p, find the best q, then find the next p by minimizing it again, then find the next q, and so on and so forth. Okay, so this is the alternating projection. So let's be much more specific. So now I want to talk about the EM algorithm in general. So the EM expectation maximization algorithm. So the EM is just the EM, that's what it's called, algorithm. As I said, it's a special case of this alternating projection, but we'll see it explicitly. So assume, now I want to be much more specific. Okay, so we have, in general, two types of variables. X, which you want to call the observed variable, what we see, and H, which are going to be the hidden variables. So these are observed, and these are hidden. One example you should all be familiar with, which is clustering. So you have, I hope you're familiar with, the k-means. I mean, all of you play this k-means already? So, for example, the identity of the cluster of each point may be a hidden variable. I don't know it. So what I see the data point, but I don't see the label. I don't see where it belongs. So in this case, X is going to be, let's say, the position in space, and H is the identity of the cluster. So in general, I can think about my, let's call this the full information, denoted by Y, so full information, or full variable. And what I'm really interested, and I assume that this particular problem, the probability of the hidden and the observed has a nice parametric form. Actually, in almost all the cases that I know, this is of exponential form, which means it has a nice sufficient statistic. So this is, so I take an exponential form, so Y is the full information, and I split it in, I think about it as split into two things, one that I can observe, and another one that I can't observe. So for example, you're given data of heights of people, and you're not told if it's male or female. Well, let's say it's a certain age, okay, to be consistent. So in general, you know that given male at age 20 and female at age 20, they have slightly different distributions. But I'm not giving you this. What you're going to have is a mixture of these two things. But if I'm giving you also this hidden information, male, female, then you'll know that one has one Gaussian, the other one has another Gaussian, probably. And then you know, if you know which Gaussian it is, it's very easy to estimate. Just estimate the mean and the variance of this population. But if you don't know, it's a mixture of two Gaussians, and this is not an exponential form, okay? As you know already. Okay, so in general, mixture distributions are very much, this is the typical case of this thing, where you have hidden information, and you average over the hidden variables, and you get mixtures. Okay? So averaging over the hidden variables is a nasty distribution in this case. I would like to split it. This is actually very, very typical. I'll tell you tomorrow a little bit about much more general class of models like this, which are called Bayesian networks or graphical models, for which we have usually hidden variables and observed variables, and we do exactly this, the EM in general, with all sorts of tricks, which is, it's a very big model, it's becoming non-trivial. Okay, so this is what we call the full likelihood. The goal is to maximize the likelihood of the observed data. So we want to maximize P of X given theta, because we don't see the hidden data. So we are given observations, and we want to find the theta maximum likelihood. Or if you want to find the theta ML, which is the argmax of log P. Now it doesn't matter. Okay, so this is the observed likelihood. not really the observed likelihood, it's the observed likelihood function. Well, likelihood function? It's the likelihood of the observations only. So allow me to ignore for a second the fact that x can be a vector or a sample or whatever, just x. Okay, so this is the goal. But this is a hard problem. Why is it a hard problem? Because it's easy if we know the hidden variables, that's what we assume. So we assume that this argmax of p, x, and h given theta is easy. Easy. It's easy, for example, typically it's exponential form. All right. So what should I do? It's actually a very simple idea, and I want to make sure that you are somehow related to this very general thing that I said so far. So what could you do? It's a special case of partial observation. Okay, I see only part of my observation. So essentially, the idea is the following. It's very intuitive, and actually one of those things that I myself tend to complicate without need, but it's really written in many different places in somewhat obscure way. So let me. So essentially, the whole point is to notice the following: P of the full data, x and h, given theta, I can always write it as what? As P of x given theta times what? Simply factorize it. So what's missing here? Yeah, it's P of h given x and theta. Okay? That's it. So now, so essentially, what I want is this likelihood. I can. So I somehow want to. So the log of this is going to be, of course, the sum. Okay. And so what I want. So what I want is to maximize the hidden, the partially observed likelihood. So log of px given theta, which is what I want, is simply log of the full information minus log of this hidden variables given x and theta. Condition. Notice that this is precisely the conditional distribution of my unknown, conditional on what I know. So this is a special case of what I said before. So this is something which I don't know. I don't know the hidden variables. So what makes perfect sense is to average with respect to this. So now let's just make it clear. So I'm going to assume that at some point I have a guess, the current guess of theta. So let's say the current guess of theta denoted by theta hen. I'll write it with, for any theta this is true. So if this is my current guess, this is the best I can do at this point. And now I want to average this with respect to the unknowns. So, but for another theta. Okay, for any theta. So take the expectation with respect to p of h given x and some other theta. I'll call it theta at this point. For theta is not necessarily theta n, any theta. Okay, so I want to separate these two things because these two variables, theta hat n and theta are going to play as my successive projections. Okay, so I'm going to, so this is very easy. There's one trick here. This is the trick. I want, as I said before, in general, if I don't know something, the best I can do is average with respect to it. Okay? Now, I don't know age. So I want to average with respect to age. But at this point, I want to modify theta sequentially. So I average with respect to any distribution like this. This is averaging over age, but I don't know exactly which theta is there. So I average as any theta. Now, averaging this with respect to the age, is it going to change anything? No, because I conditioned on x. There's nothing that depends on age there, so this is not going to change. So averaging this, so I'm going to get that the log likelihood of this theta n, let's call it just L x theta n, is log likelihood, whatever your notation is for that, is simply is going to be equal to the expectation with respect to this ph condition on x and theta of the first one, of the full likelihood, minus this function, the expectation over the same hidden variables x and theta of this. But this was my theta n. Okay, so this is true. Just did the expectation and notice that this term is independent of age. So nothing is going to change there. Okay? Yeah, sorry, this was theta n. Okay, so now just to simplify notation, what we usually do is we call this Q of theta and theta n. I think I'm confusing the order, but never mind that. This is some function. Okay, it's some function of the two thetas. Now the assumption here that this function is easy. Why is it easy? Because I mean, this is just a very simple projection. This is actually the E projection here. It just I'm sorry, the expectation is take the most likely hidden variables, average over the hidden variables of the full likelihood. But since the full likelihood, let's say, think about the Gaussian mixture case. So the full likelihood, actually, I know what age is. So it's one Gaussian. I know what age is. It's averaging over one Gaussian. This is easy. In most cases, this is a simple distribution, which means that the log likelihood is. And I average over the unknown. Okay, so let's call this Q of theta and theta n. It's actually, the notation here is a bit tricky because I used Q for something else before. Ignore it. It's a function of theta and theta n. Yeah, condition on x. You're right. No, yeah, it's conditioned on x. But so x is given. I'm not changing x. X is given all through the process. I mean, you have the data, you have the observation, and you fix it. That's what physicists call quenched. Okay, it's a randomness which is given once and for all. Okay, so so this is Q, and this function is actually you can see immediately that it's going to get some sort of a DKL eventually, but it's the expectation of one distribution of the hidden variables with respect to the previous estimate of theta with respect to a new one. So let's I don't know. You can in the booklet that we have in Hebrew, we actually wrote it as age of theta and theta hat n, but it's somewhat confusing because it's not entropy exactly. So whatever. Okay, so now what is the trick? The trick is this is easy to calculate. This is the E step. Let's optimize it. Yeah, I think you're right. I knew that I'm going to mess somewhere here. average with respect to the parameters I know of something I don't know. So this is easy, yeah, the orange. So I want to maximize now this. Yeah, you're right. You're right. This is what I assume known. Okay, so this was any theta. Sorry. This is nothing is wrong. It's except a notation. At this point, what is precise? And here I average with respect to what I know, what I think I know. Okay. Okay. So and we call this Q. I think I still call it this. Okay.
So the second line is expectation with respect to the specific frequency.
Yeah. So this is known. I know the parameter already, and this is unknown. This is actually the hard part. I don't want to deal with it because I don't know the theta, and I don't know, and the distribution of the hidden variables is difficult. But this is easy. As I said, this is usually an exponential form, and given theta is actually very easy to calculate the log likelihood. Okay. So now I'm going to define. So let's do the following. Theta n plus 1 is going to be the argmax of Q with respect to theta, Q theta n. Okay, so this is the definition, the key of the main iteration here. So I'm going to maximize this, the full likelihood, if you want, with this average on the hidden one. But this average is easy because I assume that I know the parameters here. Okay. And actually, it's not only easy because maximizing this distribution, the full likelihood is also easy. So this is an easy problem. And actually, it's related to the E step that this is the maximum step. So calculating Q is the E step. This is the E step. And maximizing it, this is the M step. Okay, so now there is actually a very weak claim that if this is my iteration, I just repeat it. Okay, so the claim is, or the proposition is that what? That the likelihood of the data, the observed data, given theta n plus 1, is greater or equal than the likelihood of the data given theta n. Okay, this is what I want to prove. Yes? Yeah. Yeah, so I assume theta n is assumed known. Okay, so this is my previous iteration. So in this case, this conditional expectation, the conditional probability can be calculated.
Yeah, but what about the log? Is the log of P of x and h, the current h you are averaging on?
Yeah, but so this is what I call y. This is the full data.
But what is the theta you are getting?
I don't know, but I argue that this is a simple form. So, for example, in the Gaussian case, I know it as a function of theta for any theta. So, if I know the hidden variable, I don't want this to be a complicated function. Okay, so but if I know the function, I'm going to maximize now over theta. So, if I give you the hidden variable, so again, keep in mind the Gaussian mixture. This is the easiest and the typical example here. If I'm telling you what h is, it's one Gaussian. Okay? So in this case, theta are going to be simply the parameters of one Gaussian, which are easy to estimate. So this is essentially, it's a maximum likelihood of the full problem average over the hidden variable. Okay, so this is this is what is going to be related to the projections again. But before I confuse you with this, let's first prove this. Okay, so this is an easy trick. So why is it true? I mean, I confused myself with the notation. Sorry about that, but it's didn't say anything wrong. It's just confusing myself. Okay, so far. So this is how I define the next iteration. I maximize this, and with only this function. So let's see why this is true. So take the difference. Lx theta n plus 1 minus Lx theta n. So this is the proof, if you wonder. I take this. So what is it? So it's the difference between these two q's. Okay. So it's q theta n plus 1 theta n minus q theta n theta n, right? Because this is my definition of in one case I put theta to be theta n plus 1, in the other case I put theta with the previous one, theta n, okay? So, and of course, minus the differences of the age of this. So it's the expectation with respect to theta n. Once I put here theta n plus 1, and the other one I put here theta n. Okay, so I can write it as the expectation with respect to this p of age given x and theta n of log. The first one is a plus, because so it's theta n plus 1, p of h given x and theta n plus 1 divided by p of h given x and theta n. Let me just see if the sign is right. So you see why this difference, the difference of the two ages, is expectation with the same thing, p of theta n. But once I plug theta n there, and the other one I plug theta n plus 1 there. Okay? So this one comes from this, with the theta n plus 1, and this one comes from this. Okay, I just saved myself one line by putting it already on the same log. So the difference in these two logs is just the difference is this when I plug theta n plus 1 here versus the one that I plug theta n there. Just want to make sure that the sign is right. Yeah, the sign is wrong. This is plus. Okay. Check it. The only thing I did here is notice that I'm actually taking the expectation is sent to the same function here, theta n. In the first case, I plug here theta n plus 1. In the second case, I plug here theta n, so I get the KL difference. Okay? So this, okay, I use this. I use this equation. The likelihood given any theta, given any theta, is this minus this. Okay. No. No, I want it to be the same theta n. Now I want to change only the theta n plus 1. No, this is what Noga was fixing here. I average respect to what I know of theta I don't know, and then I take the expectation. But now so the difference between these two things is just it's only here. It's a minus? Minus here? Let's see, it has to be negative. Okay. The whole thing has to be greater than 0. Okay. So now notice the following. This theta n plus 1 was defined to be